Hello everybody. So I'm an optical astronomer, but I will introduce today's speaker as I'm hosting him this week. So it's a pleasure for me to introduce Ivan Zolotukhin, who works in Toulouse at Institute of Astrophysics and Planetology as a postdoc, and also is a member of Sterling Astronomical Institute at Moscow State University in Russia. Ivan received his master in astronomy from Moscow State University in 2006, as far as I remember, and then he kept working there as a PhD student and received his PhD in astrophysics in 2009. And I'm proud to be his co-advisor jointly with Nikolai Shakura, who most of you probably know. Since then, he's been working on a number of projects related to high-energy astrophysics, compact binaries, and also he was responsible for the compilation of the latest release of the XMM Newton DR5 catalog. In the meantime, while he was a student at the university and a graduate student, he had a brilliant industry career in parallel, and working as an IT professional at the enterprise level. And when he was offered the job as a technical vice president of the Russian #1 internet company, he declined it in order to do science. So today he's going to be talking about the slowest X-ray pulsar in the Andromeda galaxy. It's a work that I've been participating as well. And so that's for you now.
Okay, thank you, Igor, for this introduction. Let me start today's talk, which will be devoted to a very unusual beast, which is the slowest spinning X-ray pulsar, and we were lucky to discover it far, far away, not even in our galaxy, but outside, in the Andromeda galaxy. So first of all, let me say that I'm here. I just worked with a really brilliant team, and especially without Matteo Bacchetti and Igor Shilingran, this research wouldn't work at all. And the team is absolutely fantastic, and you'll see it in a few minutes. So that's the story. This project has started, and it was motivated by now famous paper of Matteo Bacchetti and others, which was published in the end of 2014 about highly super Eddington pulsar in MH2 galaxy. So it was so exciting that immediately, probably as many other groups, I had an idea to check if there are other pulsating ultraluminous X-ray sources, which, as we now know, may be neutron stars, not black holes, like it was mostly thought before. And the clear pathway was to take all few hundred known ULXs and check if there are pulsations. Well, that's easy to say, but it wasn't that easy to do because of the amount of work to be done. And at that moment, I came up with an idea to build the XMM Newton photon database. So what I did is that I took all 7,000 or something like this observations of which were used for compilation of the XMM DR5 catalog, the largest catalog of X-ray sources ever created. And I took publicly available filtered and calibrated event lists, so photon lists, which were produced by XMM Science Survey Consortium, and were publicly available from European Space Agency archive, which is essentially a bunch of binary feed tables at FTP server. So that amounts to 100 billion photons. What I did is I organized a convenient interface which to access and extract photons with automated barycentering. And now this interface is not only available for me as a database author and organizer, and it is now available on the web, and I'll show it in a minute. So once this huge data set of all photons ever registered by the XMM Newton since 15 years of its operation was up and running, the next step was to create what I call now pulsar factory, which is essentially a piece of software, a pipeline that search for coherent pulsations by right ascension and declination. So you tell a program, you tell this program a name of XMM source, and it goes to the photon database, extracts all photons of all observations of this source, and does time series analysis. First, it does Fourier transform to get power density spectra of small data chunks of every observation. Then, if there's a coherent pulsation found in power density spectrum, it does Z-squared test, another coherent pulsation test. And if the frequencies of pulsations match between PDS and Z-square, it does accelerated search with Presto software, which is known by many of you, I think. So the software was built, and then we decided to try it, basically to debug it. And it was a crazy idea that we just took an Andromeda galaxy as a test sample because it contains 9,000 XMM Newton detections. So here's a example output of pulsar factory. So a couple of power density spectra for of different observations of the same source. Then that square test is launched automatically. You see the frequencies are very, very close between these different tests. Here's the pressed output, and you it is clear that these independent tests from independent observations support the hypothesis that there's a pulsation. This is a real output of a pulsar factory, automated software to search for pulsations in all-time XMM Newton photon database, which we saw after we launched it on Andromeda sample. On Andromeda observations. So let me digress a bit, and I show that since a couple of months this is available online. So I just click on this link, go to a browser. So here's this source, which I just showed you the output. And here's it's 35 observations obtained from 2000 to 2013. And if we go and check one of the observations, yeah, by the way, you can fit X-ray spectra right in a web browser, but I'm not going to show you. What I'm going to show you is a photon database in operation. And let me rediscover the first pulsar in Andromeda galaxy with you today. So here's a very nice JS9 tool by Eric Mandel from CFA, I think. And you see the combined X-ray image from the XMM of real observation. And if I do, no, I don't want a magnifier. I want a panner. I'll move it a little. I zoom. So every pixel on this image is in fact has a time series of photons. So here's the source on the at the edge of view of XMM Newton with distorted PSF. And if I click Get Data and also tick barycenter photons, what I do is just I extract in this green circle. I extract all photons that fell in the pixels within this circle. And the system, the photon database, knows automatically the orbit of XMM Newton satellite, so it's all built in. There's no need to install anything. I'm doing it online. So it takes this huge event list from this observation and extracts photons and barycenters it. So what we have, so corrects for arrival times to the barycenter of the solar system, so that we can study fine, we can do fine timing analysis. And it then outputs, it takes well, some time, obviously, because the procedure is very complex. But what it makes, what it outputs is a feeds file with, which is OGIP compliant and can be opened with any standard software like FTools, whatever. And then you can study it. Well, let's wait a little, few seconds more, because, yeah, you see. So out of, I don't know, 1 gigabyte file with all observations, it's now just a few hundred kilobytes file up. And what I do is just, I do simple power density spectrum with the file which I just grabbed. And I plot it. So this is a real data set of a real object in M31, which we've just processed online, and we see this peak at, let's check it, 0.82 hertz, which is exactly 1.2 second, and this is the source in Andromeda galaxy. Let me continue with my slides. So what Pulsar Factory does automatically, we just repeat it manually, and it took really a couple of minutes. So when we looked at the position of this source, we were very lucky to have it on the edge of view of one of the HST exposures. You see, it's really few seconds from the edge of view. These are X-ray positions, positional uncertainties from Chandra and XMM. So it projects next to the globular cluster, the source with pulsations in few observations. So let me digress a little and explain you the pulsar recycling concept, because it will be important for the conclusions. So neutron stars are thought to be born quickly rotating. And then during the phase of radio pulsar, they use their rotation energy to emit radiation in radio waves mainly, and they slow down till 2 second, like 1 to 10 second periods. At the same time, we observe a large population of millisecond pulsars which rotate at a few hundred hertz frequencies, and they dominate in population of X-ray sources in global clusters. So what is now generally accepted is that these millisecond pulsars used to be in accreting binaries, and their low magnetic fields are caused by, and high spins, spin frequencies are caused by accreted material which transferred angular momentum and buried the magnetic field. So the object which we just rediscovered a few minutes ago has the following properties. So it has spin period observed in many observations, a spin period of 1.2 seconds. It is quite bright, so reaching like 30% of Eddington luminosity. And the chance superposition probability of X-ray objects this bright and global cluster in Andromeda galaxy is only 10 to the minus 3. So we think this is sufficient to claim association between the two, and hence we call it XB091d, because that's the name of global cluster in Bologna catalog. So it turns out to be the slowest spinning X-ray neutron star in global cluster, and the second one being accreting, being the famous integral source in Terrazon 5 global cluster. So we were able to determine the orbital period of this binary. It amounts to 30 hours and a half, being the widest accreting binary in global cluster. And the companion mass is likely to be 0.8 solar masses if we notice that the turn-off mass for the very old global cluster, which is 12 gig-year old, in fact, is 0.8 solar masses, and we have evolution-induced accretion here, which in fact matches the estimated Roche lobe size from the timing analysis. So if we compare the mildly recycled pulsar and our new one, non-recycled, they're very similar, in fact, except that the frequencies differ by a factor of 10. And yeah, if it is generally, this one is generally called mildly recycled and we have 10 times slower, we call this non-recycled pulsar. Here's X-ray spectra, which is very hard with power law of index of 0.2. Its luminosity from 2002 to 2013 doesn't change much. It's not logarithmic scale. It's a factor of 3. And at the same time, it excludes that there's a superposition of several X-ray sources in this global cluster. Here's a very nice pulse profiles, and that was crucial contribution of Igor, because this source, being very far from the Earth, the photon fluxes for the in the XMM Newton observations is 0.1 counts per second. So 1 count in 10 spin periods, which makes it impossible to analyze. Essentially do sophisticated timing analysis with common software like Presto and Tempo. And Igor has come up with an idea to look for, to determine period by maximizing contrast of pulse shapes, and developed mathematical, statistics to quantify uncertainties of these spin period estimates, which is available in the abstract of, or in the appendix of our paper, based on classical Leahy statistics. And it allowed us to reconstruct essentially spin up, that's the spin period of a neutron star, that's epoch of observations in years, if it's more convenient. And here, so it's not possible to determine spin period because of these low statistics from individual observations. So what Igor did is he combined adjacent data sets, because over the course of 12 years there were 35 or 38 observations. And if we combine several adjacent observations separated by like 1 to month, and our pulse statistics improves, we consider that the period didn't change much between these observations, and we combine these data sets from observations separated by 1 to month in a single point, and which is these black points on this diagram. If we analyze individual observations, it doesn't give anything meaningful. This is a light curve, which doesn't show statistically significant spin-up. But with this new methodology, we're able to claim the spin-up, except for the last 2 points, which is non-trivial. I mean, this we can probably discard, but this is it a hint for equilibrium rotation or not? I don't know yet, but we'll see. So let me say a few words about the global cluster, which you see here as this blurry thing. Let me compare it with a host of the 2005 pulsar. 2005 has 2 stellar populations of these ages, and it is one of the it's #1 global cluster in the Milky Way galaxy by a parameter called encounter rate, which is known to correlate with, for instance, population of LMXBs in global cluster. And if we compare this gamma, we understand that our global cluster from the M31 has a larger gamma than the largest one in Milky Way galaxy, which means that there are a lot of stellar encounters and products of these encounters. Small gamma, which is an encounter rate per binary, which is correlated, which describes exotic products of binary breakups, for instance, is also very high for this global cluster in M31. So I'm saying this to stress that 2005 with a mildly recycled pulsar is a prolific global cluster for in terms of binaries and with neutron stars, and the M31 BO91 is even more prolific with respect to these parameters. So neutron star, we estimated that from naive assumptions, the B field is between 10 to the 8 and 10 to the 12. If we see spin up, the magnetic field is lower, tend to be lower. But if it's equilibrium, it's 10 to the 12. And it's not clear if the neutron star is young or not. That's the current state-of-the-art modeling of binaries in global clusters. And I'm showing this to remind you that in latest simulations, for instance, Ivanov et al., they find that accretion-induced collapse is crucial formation scenario of neutron stars, which are being born at all epochs of even after 12 gigayears of the life of global cluster. So we think that accretion-induced collapse may have taken place in our binary. So if you don't believe in spin-up from our data and it's period equilibrium, B field is large. And likely neutron star was formed very recently. Given that, accretion-induced collapse seems to provide 3 times more, it is 3 times more effective than all other neutron star formation channels in global clusters. And the numbers here suggested that it is 10 LMXBs per 1 gigayear, even of 2005-like cluster after 12 gigayears of its life. Also, some authors say that accretion-induced collapse fits well the population of 4 known high B field slow radio pulsars, and 1 field pulsar for U1626, which is also very slow. So we can speculate if we had accretion-induced collapse in the very same system, that it's not likely that we would still have 0.8 solar masses companion, because accretion-induced collapse would exhaust donor because the compact object had to accrete several tens of solar masses to convert from white dwarf to neutron star. And then it is known that accretion-induced collapse causes detachment of the system because of loss of binding energy, and it needs time to resume mass transfer. It may take 100 mega years easily, so the system would have disrupted, for instance, in such a dense and stellar system with a high stellar encounter rate. So it is, if we believe in long-term spin-up for the system, it means that the rate is like this. It means that in 100,000 years, it becomes a normal recycled X-ray pulsar, essentially, millisecond pulsar, and this time scale is very short, and it automatically means that we're very lucky to see it in this at the onset of the accretion, and in the very beginning of its recycling. So if you read the archive carefully, you may have noticed that this pulsar was presented by another team called Extras, which these guys study timing with XMM Newton at several time scales. So that's a large project. And they published in the end of, in December last year, they published MRS letter about this pulsar. We disagree with many of their conclusions, but the worst thing is that I doubt that it was them who discovered this pulsar. So, and I have evidence about this. So it's a not a very pleasant story about this pulsar. So we published our paper in February. Basically, it's on the archive, and we've just received a positive ref report with minor comments which we need to fix. So they published it earlier than we, but I doubt it was independent. So my conclusions, because I'm running out of time, XB091D is the second farthest extragalactic pulsar, in elements B's at least, because some people say that white dwarfs, which also sometimes are observed pulsating in X-rays, and there are few of them known in M31. Some call them pulsars as well. So these were known before, but not with these short periods. It is a slow spinning neutron star in global cluster, and it poses it is a challenge to explain it and to convincingly explain the origin of the system. It is the widest accreting binary with low mass subgiant companion, and apparently it's a missing link in classical recycling theory because it's first truly non-recycled accreting binary. And despite it looks peculiar, and because it's the slowest one of this kind, I think that accretion-induced collapse is a very plausible explanation, despite that we cannot really rule out the primordial origin of the neutron star, which should, however, conserve the high magnetic field after 12 gig years of the age of the global cluster. And I think this is important, that this result is fully reproducible online from this website, XMM-catalog, IRAP on PayU. And, well, that's just an example of studies that we do with Igor and this fantastic team. Thanks a lot.
I'm assuming that you don't have a distance estimate directly from dispersion measurement or any other way to the pulsar. So I want to ask how certain you are about the association of the global cluster, because it seems really peculiar. We don't see any of those slow pulsars in the Milky Way, even though there are a lot more data. And then you see one that's very slow, and that's the only one.
Well, if you just, for instance here, just, I mean, if you take a surface density of global clusters and the surface density of X-ray sources, which are represented by these uncertainties here, and compute chance superposition probability, it's probably 2-3 times 10 to the minus 3. So that's it. I mean, we don't know, of course, the distance. We can't determine and constrain it, but we claim association based on this number. Yeah. Which, I mean, it would be interesting to understand from the dynamical and stellar evolution and the probability of having such system, of observing such system. If it's dramatically lower than 10 to the minus 3, then yeah, we're in trouble. But I hope that it's not. Yeah, well, from naive considerations, like, I know there are 100 of global clusters in our galaxy and 400 or something in M31, and that's the first object of this kind out of few hundred global clusters, true. But no one looked at all M31 clusters, and no one did timing analysis at 1 second level of all timing search in M31, so it is to be done yet. So. But I'm talking about the X-rays indeed. Yeah.
Yes. Can you make a comment about the sort of general context? So how many did you? Is it about the progress of the search for the ULX? I guess you started that, right?
Well, I didn't quite yet. So you refer to ULIX pulsations. Well, it's that was the motivation. But I mean, this project is ongoing. That's the early result of debug of Pulsar Factory.
This was search result from how many sources?
It just, randomly chosen sample of M31 sources, let's say. And that was, there are more pulsars in M31, I mean, I can tell you, but it's just the easiest one to analyze, because it popped up with our basic pulsar factory algorithms in 3 observations, so that's why we started from this one. But there are much more, and I hope I'll have time to finish Ulix search, because now the infrastructure ready. So this is a infrastructure debug result, early one. So once it is ready, I'll launch it over the set of Ulixes. Yes. So it's not yet done.
I have a short command. If you make a binary a little bit tighter, so the period goes down from 30 hours, you won't have enough statistics to detect it.
Indeed.
So that's the point. So there may be many more like this, but if they're in sort of closed binaries, we won't be able to find them because the pulse will be smeared by the orbital motion.
Yeah, or inclination is larger than some level, because it won't be the pulsations will not be coherent anymore, and at this low photon statistics, it will not be detectable unless we'll come up with a new accelerated search one day. Yeah.
Okay, Leo, for the last quick
So if
question.
you go back to your video where you showed the pulsations.
The pulse profiles?
Yeah, this one. So you're saying that if the source was, the period was much shorter, you won't be able to pick out the signal?
If the orbital period of the binary is much shorter, we wouldn't be able to pick up the signal. Because here there's one, there were a couple of observations among 30-something where we actually detected it close to those phases in the orbit where the period didn't change during the phase. And if we hadn't seen it there, we wouldn't have seen it at all.
So your algorithm doesn't pick it out?
No.
As a
Like,
function of
for
phase
instance,
of the
here, the second to last one, you see it's a very nice pulse.
Yeah,
That's
this
a
one.
full orbit, basically. It's 110 kiloseconds. And how we found the orbital motion, we split it into 6 chunks, and we were able to see the modulation. And then we fed the rest with this orbit.